We happen to have the second speaker, Moustapha Cisse from Facebook AI Research Paris.
Yep. First of all, it was actually very interesting and will give me the occasion to point out to a few things in this area. So I will talk about deep learning in the land of adversary. Deep learning is probably the hottest topic in AI right now. Whether or not it should be the case, it's debatable, but it's really important currently. And most of the techniques that are used to attack machine learning model are basically demonstrated on deep learning models. So it's important to focus somehow on these class of functions to look into their specificities and see what makes them particularly fragile to adversarial perturbations. So these are two seemingly similar or probably exactly the same image. But if you give them as input to the state-of-the-art model trained on ImageNet, then for the first one it will be classified as a Kelpie and the second one will be classified as a Chihuahua. So these two images are just different because to the first one was added imperceptible adversarial noise. So this is an important problem, and not just because it may hurt the feelings of the Chihuahua, but also because this goes beyond plain image classification. In fact, recently with colleagues from here, Bar-Ilan University, with Yossi and other colleagues, we actually showed that you can tailor these sort of attacks for more complex structured prediction models, such as semantic segmentation. So if you think about it, this is problematic because semantic segmentation is basically what is used in a self-driving car. So the vision recognition engine labels every pixel it sees, and that way interprets the scenes and takes decisions. So you can literally make it hallucinate anything, and in here it is a minion. So you can also do it for speech recognition. So in this case, you can, if you look at the two spectrograms corresponding to two audio files, one of which is adversarially perturbed, it's very difficult to tell them apart. But in fact, if you listen to the audio, to the corresponding audios, also it is very difficult to tell them apart. Actually, we performed ABX tests where humans was asked, 100 different humans were asked to tell apart the perturbed audio and the original one, and statistically significant, they could not make the difference. What is interesting is if you add adversarial noise to this audio file, you can even attack systems that you don't have access to. For example, here, we took an audio file, we added adversarial noise to it, and we played the original audio file. We played the original audio file in front of a Google Voice, which is in your smartphone, any smartphone. And if you play the original audio file, you can see that it gets pretty nicely. The transcription is actually pretty accurate. But if you play the perturbed audio file, which a human cannot distinguish from the original one, then the Google Voice starts making all sorts of mistakes. So this is interesting because it says something about the regularities that the model learned and what may be the properties that imply this behavior. So how is this noise created? Nicholas spoke a bit about this. So basically, usually what people do is they take the input example and then consider an LP ball around this example and find in that ball a similar example. So the ball is a very small ball centered around example with a radius epsilon, which is very small, and find in that ball an example that maximizes the loss function. So if your model is very complicated, basically if it is non-convex with respect to the input, then this cannot be solved in closed form. Then you can do it in a stochastic gradient descent fashion. And depending on the norm that you consider and the number of iterations that you do, there are different flavors of solving this problem. So if the noise is constructed this way, and you have the input x, and the model, let's call it j theta here. So where is the problem? We just have inputs x and models j theta, and we add a small perturbation to the input. It completely changes the behavior of the model. So whatever happens here, the problem must be either in the input. Obviously that's where we add the noise. But if there is a solution, it must be how we deal with the input or how we parameterize the functions that we learn. So we will have a first look into the functions that we learn, so the models, the neural networks. And if we step back a bit and have a look at how we learn these models. So basically, ideally, what we would like to do is to perform risk minimization. So if we knew what was the joint distribution between the examples x and the targets y that we would like to learn to predict, we would just take a parameterized function j theta and learn to minimize the risk with respect to this distribution. But unfortunately, we don't have access to this distribution. We just have access to samples from this distribution. So what we usually do is we do empirical risk minimization, but to account for the fact that we're optimizing for a specific class of function with a limited number of data, we add a regularization term. Unfortunately, models that are trained this way are still not robust to adversarial examples. So another way of doing it is to consider a robust version of this formulation, which is instead of considering the examples x, you consider balls around the examples x and sample the worst case examples that you can find in these balls and minimize the risk to train your parameters, to fit your parameters. This works to some extent. It's actually called adversarial training, but it is still very, very fragile to iterative attacks, for example, in a white box setting. So there is an old idea, which is called vicinal risk minimization, which is actually closer to the actual risk minimization, because it just makes assumption on the factorization of the joint distribution. If we could do this, maybe it would be better than doing plain regularized risk minimization. And it is actually possible to show that the robust risk minimization is just a special case of vicinal risk minimization. But here again, the problem is that we do not know how to choose the marginals, P of xi and P of y. So if we look into the problem, we can make two observations. So here's the first one. So I skipped the details of the analysis, but if you're interested into it, you can just go and check the paper. It's called Parseval Networks that we had last year. So the term on the left-hand side is the generalization ability of the network. It basically measures how, if you train the model with a regularized empirical risk minimization, what would be its generalization ability. And the first term on the right-hand side is, so the term on the left-hand side is the empirical risk, the regularized one. The first term on the right-hand side is the generalization. And you have a product between terms that depend on the properties of your model. In particular here, one term is of interest. It's the second one, and it's the Lipschitz constant of the function that you are learning. So basically, what is the Lipschitz constant? If your model varies a lot between inputs that are very close to each other, then it typically has a large Lipschitz constant. Then if it behaves nicely, more nicely between inputs that are close to each other, then the Lipschitz constant is very small. And what we would like, ideally, is to have a model whose corresponding Lipschitz constant is actually small. So a second observation, which was made by different authors, approximately at the same time, is that if you consider the norm of the perturbation that you have to add to an input in order to change the decision of your model, this is basically upper bounded by a term that depends on here, this term. It's basically the cross Lipschitz constant of your model. It's typically similar to this. So what these two observations say to us is that if you want to control your model in order to make it robust to small perturbations, you need to control its smoothness. You need to control how robust it will be to how smoothly it will behave when you add small perturbations or when you consider inputs that are very close to each other in the input space. If you want to do it analytically, this is very, very difficult to do. But there is an algorithmic way of doing it, which is a secret sauce we call here mix-up. So this is a very simple, very dumb idea, which works actually pretty well. Surprisingly well, actually. So it just consists in, instead of training your model on individual examples, you take pairs of examples, take convex combination of the examples, and convex combination of the corresponding outputs, and train the model to predict those. So for example here, normally what you would do is to train, to show this example on your network, to your network, and say to it, this is a cat. And train the model to predict a cat. And similarly, you should do it for the dog. But instead what we do here, we take an image of a cat and an image of a dog, and we mix them in the pixel space, and we ask the model to try to predict to predict that this is 40% of a cat and 60% of a dog. This is a stupid idea, but actually you can explain why this should work mathematically. It makes a lot of sense, but at first it looks really stupid, and it's very simple. It's 2 lines of code. You just change your code, 2 lines of code, and you try this, and it turns out that it works really well. So what's going on here? If you train a model this way, and you take pairs of examples, and you measure the norm of the gradient of the loss function with respect to the input, you can compare what's going on if you train your model using a regularized empirical risk minimization versus if you train your model using mix-up. So you can see clearly here. So this is the mixing parameter, basically. So you take x1 and x2. You do lambda x1 plus 1 minus lambda x2. So this is the value of lambda here. So between any pair of points, what happens is that the norm of the gradient of the loss function with respect to the input is actually very small. Which means that if you take a pair of examples and draw a line between those examples, if you go from one example to the other, the variation of the function is actually very small. It doesn't change really quickly. And the same holds actually for the loss function. So we actually tried this and train a model to see whether it would make the model more robust to adversarial example. So ERM here is the traditional way of training the model with stochastic gradient descent, with regularization. So if you measure it on white box attack, so FGSM is the fast gradient sign method that Nicholas talked about before. So you can see here that, so lower is better. That mix-up is substantially more robust to adversarial examples than ERM, right? And the same holds for black box attack. In fact, in black box attack, it's even better. But in both cases, you can see that if the adversary has full information about your model, basically if the adversary has access to your model, to all the parameters, then it can have a 99% success when it attacks your model. And the picture is just slightly better for the black box attack. So what's going on here is actually that because of the over-parameterization of the model, there is some limit to what you can achieve as far as robustness is concerned by regularizing your model or by acting on the properties of the model. So namely here the Lipschitz constant of the model. Nevertheless, this has many benefits, training the model this way. In fact, it also makes the model more robust to perturbation of the output. So if you had an adversary that would, while you train the model, flip the supervision in order to poison, to do poisoning, data poisoning attacks, this way of training the model is much more robust than the baseline. First, the regularized risk minimization, and also the different ways of using dropout in order to be robust to these attacks. So we also tried this approach on other types of data which are not images, and it works just fine. In fact, it actually improves the accuracy of the model. So if you take your favorite ResNet and run it on CFAR, training your model this way, besides the robustness, what you gain is actually improved accuracy. So these are state-of-the-art results on these data sets, basically. And if you consider the ImageNet benchmark, just taking your favorite model, changing two lines of code, gets you state-of-the-art results just by doing this. Right. So there is some benefit in trying to control the properties of the model. But there is still some limitation in doing this. And I think this route of trying to improve the robustness to adversarial examples by acting on the parameters, not only it has slight benefit, actual benefit, but also it allows us to gain more insight into what's happening here. So people have also used it to stabilize the training of GANs, but I will just skip this. So I think this perspective, the first part, which is using, looking into the properties of the model in order to improve the robustness, is actually interesting, but it does not solve the robustness problem. So the second route, the second path that people have not explored a lot is how to act on the input in order to make the model more robust. And by how to act on the input, I mean independently from the model. How can you use a transformation which is agnostic to the model and which ends up making the model more robust, or which ends up making the whole process more robust to adversarial perturbations? So there, if you consider images, there are various types of transformation that you can perform. So you can, for example, do lossy compression. If you do JPEG compression, it is supposed to remove some of the noise that may be added to the example. Okay. You can reduce the depth of every pixel, right? Instead of representing it in 64 floats, you present it in 32 or 8, or just reduce that. Another thing you can do is, instead of classifying on the image, the full image, just crop the image and resize it and perform your prediction on parts of the image. Actually, we have tried all of these things, and these, in particular, these two are very ineffective. This one works to some extent, but I would like to discuss these two transformations. So the first one, which is the total variance minimization, consists in randomly, given an input image, randomly dropping some pixels, zeroing them out, basically. You just draw from a Bernoulli for every pixel and zero it out, whether or not it's successful. And then reconstruct the perturbed input with a constraint on the smoothness of the image. So basically, you add a total variation constraint to this optimization. And this term is just equal to this. So this is pretty well known in compressed sensing. It's actually convex in Z. So there are efficient solvers based on split-Bregman methods to solve this. Right. This is included in any image processing package, basically. It's very, very standard. But it turns out that it can be pretty effective. So the second thing you can do, it's an old idea, but it's also very effective. It consists in, given an input image, to synthesize a completely new image by drawing from a database of image patches and replacing the patches in the image with those patches drawn from a private database of image patches. The effect of such transformation is that it wipes out completely the noise that is injected in the image. So you just take an image, divide it into patches, take every patch and replace it with perform a randomized nearest neighbor with a private database of patches that you previously constructed, and use the newly constructed image to perform your prediction. Right. So this way of doing the transformation has several interesting properties. And one is that the synthesized image only contains non-adversarial pixels. Because the image that you're seeing is a completely modified image. The second one is that the transformation is non-differentiable. So even if the attacker could access the database, the private database, it would be difficult to integrate the database into a differentiable process in order to construct the model. And the third thing is that it adds a layer of security, because you can consider that the database of patches is kind of a secret key, and it complies with the Shelf law. So typically, this is what happens. So if you have this image originally of a bug, right, and you apply a TV minimization procedure as I described before, right, and also a quilting procedure as I described before, you take the same image, create an adversarial version of it, and to this adversarial version you apply the TV minimization, and you also apply the image quilting. If you take the difference between these two images and these two images and these two images, so you have them here, you can see that this corresponds to the adversarial noise. But when you apply total variance minimization, you can see that all the adversarial noise that is present here is completely wiped out. If you compare these two images. And most of the difference between this image and this one is actually on the object itself. And it's not even clear whether this corresponds to adversarial noise. And the same thing happens, but in reverse, with the quilting procedure. The structure of this is very different from this. And it's very unlikely that this will be adversarial to the network, as I will show later. So, if you take a model that is already trained on pairs of inputs like this, x, I, y, i's, and at test time, instead of showing x, I, y, I, you show a transformation of x, and you measure the loss with respect to y. So typically here the model sees a distribution of example which is different from the distribution of examples that it was trained on, because the statistics of the modified images are different from those on which the model was trained on. But still, you can see that. So here, this is the strength of the adversary. So it's the norm of the perturbation, and this on the y-axis is the performance of the model. So higher is better. This line is the reference performance. So it's the performance of the model on the clean example. And this line, the red line here, is the performance of the model when it uses no defense strategy. So you can see that just by performing these transformations, so this in red, you have the cropping ensemble, which is pretty effective in this case, with all the attacks. So these are different attacks, right? In blue here, you have the quilting and the total variance minimization. And in green and red here, you have the compression techniques. So cropping, total variance minimization, and quilting are already very effective, even though the model was not trained on images that are transformed this way. So when you see this, the next step is just, instead of training the model on X's, train them on transformed examples. And in fact, when you train the model on transformed examples, the performance at test time on transformed example is much higher than before compared to here. And it is possible to improve these results just by ensembling these methods. So it's also possible to perform white box attacks. It's not exactly white box because the attacker doesn't have access to the database of patches in the case of quilting, for example. But it still complies with Kirchhoff's law because the attacker has access to all the parameters of the model. And still you can see that the model is very robust compared to data science. So we compare this defense strategy to what is considered in the literature as being the state-of-the-art defense. In fact, this defense, which consists of an ensemble adversarially trained model, where you train your model by generating adversarial example using a set of existing model in order to account for the fact that at test time your model will probably see other adversarial examples. It is very, very fragile to sophisticated iterative attacks. It works well with one-step attacks, but it's very, very fragile to sophisticated one-step iterative attacks. So we compare this approach to the method I just described. And as you can see, for each of these attacks, it is much, so higher is better here. So for each of these attacks, it's much more robust. So orders of magnitude more robust, actually. So when there is no attack on the clean examples, the performance here is lower because the model here is is a smaller model than the model used here. So this is just a ResNet 50, and this is what is called an Inception V4, so it's a much bigger model. So you can increase this performance just by ensembling these three defenses, which gets you to 51% accuracy with a very strong attacker, compared to the 1.84% accuracy that you will get with the ensemble adversarial training model. So, image transformation and actually input transformation, because whatever I have described here can be extended to other types of modalities, especially speech. You can do quilting with speech. It is orthogonal to all the defenses that do exist, so you can combine them. It is agnostic to the model. It doesn't make any assumption about the model that you're using. It doesn't make any assumption about the adversary the model will be exposed to in production. And it achieves state-of-the-art results. So if you want to test it, the code is available online. You can just download it and test it against any defense that exists. It's much, much more robust than whatever you will find. And the method is described in a paper that is available on arXiv. So I would like to talk a bit about adversarial examples, but beyond the security and beyond the accuracy problem. What can we do with adversarial examples? How can they be useful? We have already seen in the first part that we can use them in order to gain more insight into the properties of the model. But that was basically analytical. So what can they tell us about the data they learned from and the predictions that they are doing? So we performed a few experiments, which I would like to share with you. And the first of which is to take test examples and make predictions and explain those predictions. So I will not elaborate on how this explanation is obtained, but basically the general idea is to find what the model focuses on when it makes its prediction. There are different ways of doing it, but that's the general idea. So you submit this example to your system and it says that it's a JIT. And when you ask an explanation to your model, it says, I say this is a JIT because this is what I saw. To me, this is what is important. And you take the same example, add adversarial perturbation to it, and now the model predicts ambulance. And when you say, why do you predict ambulance, it gives you this explanation. So there are two things here. The first one is that the noise that you have added that modified the prediction of the model mainly shifted the attention of your model to different parts of the image that were not important in the first place, but that suddenly became important. And the second thing is that if you take a popular data set like ImageNet, which is a data set of images, natural images, sampled from the web, about 25% of what we consider being misclassifications that are due to adversarial examples are actually not misclassification. Because the ground truth is considered to be a JIT, but if the model says that this is an ambulance, it can also be considered true. So the metrics we use to evaluate the models should probably be revisited. So a second experiment we performed is to assess whether humans are any better than these models. So what we did is that we took examples, images, to which we added adversarial perturbation and performed prediction with state-of-the-art models. Then we gathered the explanation of these predictions and submitted the explanations to humans and asked them to tell which class, which category the image belongs to. So for example, this is a picture of an ambulance, so the ground truth is an ambulance. But when we add adversarial perturbation to it, the model says that this is a police van. So if we show this image, the same image, if we show it to 5 different humans, only one of them, one of the five different humans, will say that this is a police van. But if we show to the humans the explanations that the model gave us, rather than this image, what happens is that all the humans, 5 over 5 humans, agree that this is a police van. And the same thing holds for each of these things. So this is a beer glass. And when you add adversarial perturbation to it, the model says that this is a honeycomb. Right? But when we show the explanation, which is basically what the model actually sees when it makes its prediction, to 5 different humans, all 5 of them agree that this is a honeycomb. And to me, this means that if the humans look at the images the same way that the computers do, they will just make the same mistakes. So I'm not sure we are really better. So a third experiment we performed, in order to have a different use of adversarial examples, is to use them to exhibit the biases that are present in the data and that the model have picked up while learning from the data. So if you consider the way we generated the adversarial examples, we iteratively add perturbation to them until the model flips its decision. So in a sense, the number of steps or the magnitude of the noise that you need to add to an example in order to change the decision of a model is a proxy for how typical the example is for a given class. So if you have a picture with a ball centered on a ball with a white background and a red ball, if you train a model to predict that this is a ball, it will be very difficult to change its prediction because there is no ambiguity. So the example is very typical. So conversely, if you have a picture with a lot of details in it, with different objects and ambiguity, it will be more easy to change the prediction of the model by adding a little bit of noise. So we use the number of steps that you need the number of basically magnitude of the noise, which is the number of gradient steps that you have to perform in order to flip the decision of the model, as a proxy for the typicality of an example. So if this number is small, then we consider that this is a critic, right? A criticism to the model, which means that the example is very close to the decision boundary. And if the number of steps that you need to perform is large, then the example is prototypical to the category that was predicted by the model. So what did we learn? So we used state-of-the-art models that are available online, trained on ImageNet. We picked a class, which is basketball, for example, because I sometimes play basketball. And what we saw is that these examples are considered as being typical to the class basketball. And these examples are considered as being criticism to the class basketball. So you can sample many more examples, but overall, when you sample prototypes and criticisms, what you observe is that the model considers that what is prototypical to the class basketball is a picture with mostly black players. And what the model considers as criticism, so non-typical to the class basketball, is pictures with mostly white players. So you could say this is probably due to the fact that the data set may be imbalanced. In fact, it's not true. If you take the data set and the pictures that are labeled as basketball, in about 52 or 53% of them, you will see black players. And in about 55% of them, you will see white players. But what happens is that if you take the data set globally and not just the class basketball, then the black people that you will see in the images overwhelmingly appear only in the class basketball. So that's what the model has learned. And if you are not convinced, I have done the same study with Asians and ping pong. And the model basically classifies every Asian as ping pong. And the next slide is not a joke. It's actually a real example. I draw two images on the internet, pairs of images on the internet. And as you can see here, these two images, this is a person with a red shirt playing football. This is a person with a red shirt playing football. This is an African, this is an Asian, and it says ping pong here with 73% confidence, and it says basketball here with 23% confidence. And you can see the same thing happening here, here, and everything. And if you don't know these guys, you probably know these two. So I don't know if Xi Jinping, the president of China, plays ping pong, but I know that Obama sometimes plays basketball, but this is definitely not a basketball. So as a conclusion, when I look at the robustness or fragility of these models to adversarial examples, what I would like to say is that don't get mad at your models. They're still babies. If you looked at the images the same way they see them, you probably would make the same mistake as the experiment have shown. We tend to overestimate the capabilities of the models. They are very accurate, but they are not intelligent. There is a big difference here. And the second thing is that adversarial examples are not just a threat. In fact, they can be very useful to assess the biases that are present in the data and to explain the decisions that the models make. So if you want to know more about the details of this study, the paper is also on arXiv. So if you have questions, I will be happy to take them. So this is what I've presented here is mostly joint work with colleagues from here, Barilan. An intern I had last summer came from MIT and other colleagues from Cornell University. Thank you.
I have a question about the quilting idea.
Yes.
Basically, you have a very large database of typical patches, and then you move every patch in your real image, test image, to the nearest neighbor patch. This is very similar to error correction. So instead of having a database, why don't you perform data correction with a secret error correction code on each one of the patches, and then it will eliminate all the small changes that someone had made there. Did anyone check this?
Actually, this is an excellent question. I tried this, but I'm sure I did it wrong because it did not work. But it's an idea. I think I actually have discussed this probably with Yossi or Yossi before. I actually realized Yossi is a very common name.
So do you think it could work?
To me, it should work. I really have a lot of faith in this idea. But I could not make it work yet. So if someone can make it work, I will be very happy. But I will try again. Definitely.
I have a question on total duration. So I think, to me, it's just smoothing, right? You just reconstruct the image. You can kind of apply filtering, like average or median, something like that. And it was shown to work quite well to remove 60% of the noise. And training on it helps to this specific network, but you can create new adversarial examples for the new one, a newly trained network.
Actually, even if you create adversarial examples for the newly trained network, it doesn't change the robustness. Because, in fact, what is nice, what I find nice with the image transformation-based procedures, is that they're agnostic to the model. You could transform them, doesn't matter. You do it separately. When you do adversarial training, for example, you pass your example to the model, generate the noise from the model, add it to the example. So the noise itself, you're making a very strong assumption about the adversary. But here it's completely agnostic to the model. So even if you do it with, even if you, after training the model with this type of transformation, you generate the adversarial example with the new model, that's actually what we did, it's still very robust.
And another question is, for these biases, what kind of adversarial example did you use? Because if you use targeted adversarial...
No, I did not use targeted adversarial examples. Yeah, so the idea here was just to measure if an example is near or far from the decision boundary. But since the classifier is nonlinear, it's very difficult to measure it. So we used adversarial, the iterative procedure of generating adversarial example as a proxy to get that distance. That was it.
So let's do more questions on time. So let's take